Today we have the privilege of listening to Sunny Vagnozzi from the University of Cambridge, Kavli Institute for Cosmology. And today he's going to be telling us about searching for dark energy off the beaten track.
Thanks, Precious and Tony and Ninja for the invitation. So today I will talk to you about ways to search for dark energy off the beaten track. And what I mean by off the beaten track is really away from the standard ways we try to search for dark energy. So what's dark energy? We know dark energy makes up roughly 3/4 of the energy budget of the universe, okay? And what I'll tell you today are two different ways of trying to understand dark energy's properties. In the first part, I'll tell you about something I call direct detection of dark energy. It will be clear later why I call it in this way. And in the second part, I will take a more model agnostic stand and try to understand about early and late dark energy using consistency tests of our lambda CDM model. When I say early and late, the demarcation between early and late is set at recombination, so the time when the CMB form. Just as an aside, I want to highlight the work of early career researchers. So whenever I show my collaborators, if their name is in blue, this is a student, and if it's in red, it's a postdoc. Okay, so before going off the beaten track, let me just very briefly summarize what I think is the beaten track. So what are the main ways we're going after dark energy? So I'm simplifying quite a bit here, but the main route towards understanding dark energy in today in cosmology is to go after gravitational signatures of dark energy. So what I mean by gravitational signatures, this is the signatures of dark energy's energy density, both on the background expansion of the universe and on the growth of structure. And in fact, we first discovered dark energy by measuring the background evolution using type 1a supernovae in 1998. And a lot of focus today is going into trying to nail down the dark energy equation of state, W. And this is given by the ratio between dark energy's pressure and energy density. So for a cosmological constant, which is the simplest, but also very fine-tuned model of dark energy, this number is equal to -1, which is remarkably consistent with observations, as you can see down here. So simplifying quite a bit, this is the beaten track. Let's go after gravitational signs of dark energy with standard cosmological probes. By standard, I mean like type 1a supernovae, galaxy clustering, the CMB, and so on. How do we go beyond this? Let me take a step aside and think about how we look for dark matter instead. So we first learned about dark matter in the 1920s, in fact, through its gravitational signatures. Although it was really only in 1970 that the community really convinced itself that dark matter is out there, thanks to the work by Vera Rubin and collaborators. So now we are convinced we've seen the gravitational signs of dark matter. The state of the art today in searching for dark matter is to look for its non-gravitational signatures, okay? So you might have seen this schematic Feynman diagram many times, especially in particle physics talks. And what this is telling you is different ways of reading this diagram give you different ways of searching for dark matter in different experiments. So if I read it from bottom to top, what you see is you get dark matter scattering off normal matter, and this is called direct detection. So you look for the products of this recoil. If I read the diagram from right to left, you get dark matter which is annihilating or decaying into normal matter. So you look for the products of this process, which can be neutrinos, high energy cosmic rays, or photons. And you can also read it from left to right, and you can get production of dark matter from normal matter, for example, in colliders. Okay, so in this talk, I'm going to be interested mostly in direct detection in the first part, which I recall is the scattering between dark matter and normal matter. Okay, you look for the products of this scattering. So the question is, okay, this is the state of the art for dark matter. Can we do something similar for dark energy? And the first question you have to ask yourself is, okay, this relies on dark matter and normal matter talking to each other. So if you want to do something similar for dark energy, you have to ask yourself the question, can dark energy and visible matter talk to each other in first place? Well, the answer is generally yes, because whenever you have, assuming dark energy is due to a new degree of freedom, it's generally impossible to keep it completely decoupled from the standard model, unless you have some symmetry protecting this coupling. So the point is, if dark energy is due to a new particle, this is inevitably going to talk to visible matter in some way. And this is both a curse and a blessing. It's a blessing because if they talk to each other, we can try to look for it. We can try to look for non-gravitational signs of dark energy. But it's also a curse because if dark energy is a new particle, it has to be extremely light. It has to have a mass which is of order the Hubble scale or lighter. And typically it's going to have gravitational strength coupling to matter, again, unless it's protected by a symmetry. Now, as was first realized in 1998 by Sean Carroll, this leads to an immediate obstacle, which is long-range fifth forces. So you get fifth forces mediated by dark energy, which are operating on very long ranges. And this is a problem because, of course, we know that at least on local scales, Einstein's gravity works really well, and we have not seen any sign of fifth forces. So we need to hide any fifth force due to dark energy. How do you do this? Okay, so if you stare at the expression for a fifth force, you see generically you have at least 3 different ways you can hide the fifth force. And I'm going to be interested in ways which are not fine-tuned, okay, where I don't fine-tune the coupling strength or the range of the force, but I want to look at ways of hiding the fifth force, which hide it dynamically based on the environment. And these are called screening mechanisms. So you can play with the coupling in such a way that the coupling scale becomes very large. So your fifth force becomes weakly coupled in dense environments. And that's what you get in models of symmetron screening. You can play around with the inverse square law, and that's generally what happens with the so-called Weinstein screening. Or you can play around with the range of the fifth force, and you can play in such a way that the fifth force becomes dynamically very short-ranged in dense environments, okay, so in order to satisfy a fifth force test. And that's called chameleon screening, and that's going to be the one I'm interested in the first part of my talk. Just to mention, chameleon screening was first proposed by a South African physicist, Amanda Veltman, who is now in Cape Town, together with Justin Curry in 2004. So how does chameleon screening work? So say I have a scalar field, which is very light, ultra light on cosmological scales, and it has a certain potential. What you want is for your field to no longer respond to the bare potential, but to an effective potential, which you see depends on the coupling of the field to the local matter density, rho m. So what happens in this case, so the mass of the field is essentially determined by how steep is the potential around the minimum, the effective potential. And you can see this here. This curve here is the effective potential. When your local matter density is higher, this straight line is steeper, and therefore your potential is steeper around the minimum, and therefore your field is heavier, which means that the range is shorter, okay? So essentially in denser environments, your chameleon field becomes heavier, and therefore your fifth force is very short-ranged. So in a very schematic way, what you want is a field which has a long-range fifth force out in space on cosmological scales, but it's very short-ranged on Earth. Okay, so now the question becomes, okay, we know that we can couple dark energy, if it's a new particle, to visible matter, provided we have some form of screening mechanism. So the question is, can we actually go and detect screen dark energy on Earth using perhaps experiments which are otherwise devoted to searching for dark energy, for dark matter? And this is the question we try to address in this recent paper. So the question we ask is, there are big underground experiments which are searching for dark matter with this direct detection technique. The question is, can we use these experiments to search for dark energy instead, screen dark energy? And we consider chameleon screening for concreteness. So how does this work? So there are 2 parts. We need a production process and we need a detection process. So to produce the dark energy, what we consider is a possible coupling to photons. You can get a coupling to F squared, this coupling over here. And you can also couple field derivatives directly to the field strength tensor of photons. This is this formal coupling over here. What this allows for, this coupling between photons and dark energy, allows you to produce dark energy particles in very strong magnetic fields. One example is in the sun, between the radiative inner zone and the outer convective zone. There's a turbulent zone known as the tachocline, where you have very strong B fields of order 30 Tesla or more. And there you can essentially convert photons into chameleon particles. Now, these particles are going to travel to Earth, and then they can interact with normal matter in dark matter direct detection experiments. How is this going to work? So we consider a generic class of couplings to lowest order. You can couple your chameleon field to the trace of the energy momentum tensor of whatever particle you're interested in, for example, electrons. You can have a kinetic conformal coupling, where you couple the trace to the kinetic term of your scalar field. Or you can couple your field derivatives to your energy momentum tensor. That's called this formal coupling. So this is sort of a generalized chameleon coupling. And what this gives you is a process which is very similar to the photoelectric effect. So essentially you get an electron which gets hit by a chameleon and is emitted at a higher energy. So what you can look for is this energy difference, this recoil energy over here. And this is very similar to the photoelectric effect, where you have a photon over here, or to the so-called axioelectric effect, where you have an axion hitting your electron. Now, how is this relevant to experiments? So one direct detection experiment recently saw an interesting excess, and this is xenon 1 ton. It's a big experiment based underground in Gran Sasso in Italy. So they saw an excess of events in the KV region, around 2 to 4 KV. So they saw about 50 more events than they would expect from the background, which is the gray line. Now, one of the most in vogue explanations for this excess was due to solar axions, so light pseudoscalar particles produced in the sun. And this gives you a very nice fit to the excess, which is this red curve over here. Now, the problem with the axion explanation is that it doesn't stand the test with observations from the astrophysical side. Because if the sun produces enough axions to explain xenon, denser stars, such as white dwarfs or red giants and so on, are going to produce many, many, many more axions, and they are going to cool very fast in conflict with observations. So the axion explanation for xenon 1 ton is in roughly 20 sigma tension with stellar astrophysics. If we consider instead solar chameleons, so chameleon particles coming from the sun, we get this the blue curve, which fits the excess relatively well. It's roughly 2 sigma preferred over the background, but it's immune to the problems faced by the axion. Precisely because of screening, you can arrange your parameters in such a way that you produce chameleons in the sun, but not in denser stars, because chameleons are screened inside these denser stars. So the takeaway message is we can search for screen dark energy in these big underground experiments devoted to searching for dark matter instead. So we can really, kill 2 birds with 1 stone. We can search for both dark matter and dark energy in there. And you see, they have also different features in the resulting event rate. So you can actually hope to distinguish these different scenarios. Now, of course, we don't know whether the xenon result was a fluke or was a genuine detection. But if it's a genuine detection, you would expect to see the same signal in future experiments, such as LUX in America or Panda in China. You expect to see it at much higher significance. So we'll know in the future, in the next 5 years, if this is real or not. And if it's dark energy, we can hope to see it again at a higher significance. All right, so if this is really dark energy, how can we convince ourselves we've really seen a particle which is driving the expansion of the universe on cosmological scales? Well, the only way to be sure is to look for complementary signatures on cosmological or astrophysical scales. So one relevant question is, if dark energy and visible matter talk to each other, if they scatter with each other, with a rather large cross-section, what do we expect to see in cosmology? This is a question we asked ourselves about 2 years ago in this paper with Luca Visinelli, Olga Mena, and David Mota. The answer is that, surprisingly, even if dark energy and ordinary matter scatter with each other with a large cross-section, at least on large linear scales, you won't see anything. Let me show you what happens exactly. Let's take the Boltzmann equations for the baryon velocity field and the dark energy velocity field. So if we assume these two fields scatter with each other, you modify the standard Boltzmann equations by these additional terms in red. And you see this term depends, the sign of this extra term depends on the dark energy equation of state. So whether it's quintessence, so above -1, or phantom below -1. And this term is here due to energy momentum conservation. And the strength of the scattering depends on your cross-section, sigma. So we play the following game. Let's imagine cranking up this cross-section, sigma, to a very large unrealistic value, which is, for example, the Thomson cross-section. The Thomson cross-section is the value of the cross-section for scattering between baryons and photons in the early universe. So let's assume that dark energy and baryons talk to each other with such a large cross-section. What are the effects in the CMB and the large-scale structure? In the CMB, focus on the green curve. You don't see any change by eye in the power spectrum. If you look at the residuals are at the percent level in a region which is completely dominated by cosmic variance. So there's no way you are ever going to see this. In the matter power spectrum, on the right-hand side, the effects are even smaller. The residuals are at the per mil level. So it's something you have no hope of seeing, at least in a linear regime. What do I mean by linear regime? I mean large scales, so small wave numbers k. Now, the hope is that, okay, we cannot see anything on linear scales, but maybe if we go to non-linear scales, we can hope to see something. We need to go to large wave numbers. Now, the thing is, if you want to go to non-linear scales, you cannot trust a linear Boltzmann formalism. You need to actually run n-body simulations to predict what's going to happen over here. So that's what I'm doing with a student of mine in Munich, Fulvio Ferlito. We are running n-body simulations where we allow dark energy to scatter off visible matter. And we're trying to understand what happens on non-linear scales. And these are very preliminary results, but we're finding interesting things. In particular, as you see here, if I take a quintessence-like dark energy with equation of state above -1, the scattering gives you a suppression of power on small scales. And on the other hand, if I take a phantom dark energy, it gives me extra power on large scales. Now, this suppression on large scales in the nonlinear regime becomes actually an enhancement of power. Okay, you get this turnaround in sign in the residuals. And we are still trying to understand this, but we think it's due to the role of angular momentum when structures collapse on nonlinear scales. So just to give you a visual idea of what's going on, let me show you some snapshots of our simulations. This is a lambda CDM simulation over here. And what we do then is we crank up the cross-section for the dark energy interaction to 100 times the Thomson cross-section, which is very unrealistic, but it's just to exaggerate the effects. So if we take a quintessence-like dark energy component, you see, as I told you before, we suppress power on large scales. In fact, you can see in this zoom-in box, the structure is slightly less clustered. And if we take a phantom dark energy component, you see structure is slightly more clustered, so you have more power on large scales, okay? And we are still trying to understand what's going on small scales here. So the point is, if dark energy and visible matter talk to each other, we can try to really go after the signatures with small scale clustering of the large scale structure, really over here, where you can get order 100% changes in your power spectrum. And besides large-scale structure clustering, we're looking at other types of observables, such as halo mass function, halo density profiles, baryon fraction profiles, or even systems like the bullet cluster. Because now, if you get dark energy talking to visible matter, you will get a separation. Dark energy is going to pull away the baryons from the dark matter profiles. And so you can hope to see some difference in systems like the bullet cluster, where you see a clear separation between gas and dark matter. This is all ongoing work, so hopefully there will be more in the next month. So I've come to the first half of my talk, and I hope I've convinced you so far that there's, in my opinion, lots of potential to search for non-gravitational signatures of dark energy, both on Earth in experiments which are otherwise searching for dark matter instead, and even in cosmology and astrophysics if you go to nonlinear scales. Okay, so far I focused on a quite specific model of dark energy, generic in the sense that I assume a scalar field which is very light on cosmological scales and is screened locally. Now, let me take an even more model-agnostic approach and ask, what can we learn about dark energy on cosmological scales, both at early times and late times, in a way which is as detached from any model as possible? And one way may be through the Hubble tension. So I guess most of you are familiar with the Hubble tension. It's a mismatch between different measurements of the Hubble constant from local measurements, such as calibrated supernovae, and from the early universe, like CMB and BAO and Hubble flow supernovae. Now, there are many, many proposals for models which can alleviate the Hubble tension. I think it's fair to say that no model really works well, and a few of these models are really motivated. And so I think rather than proposing many ad hoc models, it's important to take a step backward and try to look at the Hubble tension with a different set of eyes and ask ourselves, why does lambda CDM actually fit the data so well? If we forget the Hubble tension, we must not forget that lambda CDM is a remarkable fit to a wide range of data. And from my point of view, I think this motivates consistency tests of lambda CDM, both at early times and at late times. Let me go through early times first. And this is particularly important because if you take the Hubble tension seriously, it looks like it calls for a substantial amount of new physics at early times. By early times, I mean before recombination. Why is this the case? Well, if you want to solve the Hubble tension, what you want to do essentially in this left-hand plot is bring the Planck contours over here to the X. And the way to do it is to reduce your sound horizon by about 7%. The sound horizon is the amount sound waves could travel in the early universe. And therefore, to reduce the sound horizon, the most direct way is to increase the expansion rate just before recombination. Okay, so you need some form of early time new physics. One very popular way of doing this is so-called early dark energy. It's essentially a switch on cosmological constant. So you get a cosmological constant just before recombination, which then decays faster than radiation away. Now, what bothers me when I look at this solution is that if you want to solve the Hubble tension, you need a lot of early dark energy around matter-radiation equality. What do I mean by a lot? You need roughly 12% of the energy of the universe around equality has to be in the form of early dark energy. That's a huge amount. So the question is, if there's so much new physics around the time the CMB formed, why are we not seeing it in the CMB alone? Why, if you take Planck's data is remarkably in agreement with lambda CDM. Why don't we see any sign of new physics? So this is why I motivate consistency tests of lambda CDM. And I'm going to talk about a particular test I proposed in a recent paper, which came out last month, based on the so-called early ISW effect. So what is the early ISW effect? If I write out, this is the usual line of sight approach to deal with CMB anisotropies. You can decompose your anisotropy on the sky in a series of different physical contributions. You get a Sachs-Wolf contribution. This is essentially relative blue shifting or red shifting of photons on the CMB surface. You get a Doppler contribution. This is a velocity term. You get a polarization term. And what I'm interested here in is the so-called ISW effect. This is the integrated Sachs-Wolf effect. And it comes from the time variation of potentials at any time. Now, phi and psi are the two Newtonian potentials. They appear in your perturbed line element, ds squared, in Newtonian gauge. You know that in a fully matter-dominated universe, potentials are constant. So this term is zero if the universe is totally matter-dominated. And therefore, you can only get an ISW contribution at 2 times, either in the very early universe, when you have a lot of radiation around, and that's called the early ISW effect, or in the late universe, because you have dark energy, which makes potentials decay. I'm going to focus on the early ISW effect over here. And why do I think it's important? It's important because if I have a lot of new physics, like early dark energy, lying around at the time of equality, it's inevitably going to affect the early ISW effect. And how can we test this? Let me take this term here, the first part of this integral. What's the most naive thing you can do? You can put an amplitude in front of it, this A EISW. Then you can go and ask the data. Is this number consistent with 1? Okay, if I take Planck data, for example. And this is a consistency check. Now, for those of you who are more on the cosmology side, this should look very familiar. It's very similar to a parameter used a lot in Planck called A-lens, which tests whether the amount of lensing you see in the CMB power spectrum is consistent with your expectation. So the question here is this number A EISW consistent with 1? If I take Planck data alone, the answer is yes, it's remarkably consistent with 1. If I constrain this number, I get 0.988 plus or minus 0.027. So it's really close to 1. Another relevant question is, when I extend my lambda CDM model to include this extra parameter, are any of the other 6 parameters going to shift a lot? And the answer is no, as you can see here. All the other parameters are really stable. The largest shifts you get are for the baryon density, omega b, and the scalar spectral index, ns. And you see they move by no more than 0.3 sigma. So the answer to my consistency test is that Planck data is remarkably consistent with the early ISW amplitude predicted by lambda CDM. Now, this is it sets a very stringent requirement for any new physics. And let me show you one example based on early dark energy. Now, why does early dark energy work? It works because you can fit the CMB basically as well as lambda CDM. You can see the residuals over here. They are no more than 10%. And here you have a huge cosmic variance limit. And you can do this using a higher value of the Hubble constant. You see 72 instead of 67. But this comes at a cost. And the cost is you need to increase your dark matter density by about 20% from 0.11 to 0.13. And this increase in the dark matter density is the reason there's been a lot of debate recently about whether early dark energy really works. And what's the big deal here? The big deal is that if you increase omega c, the dark matter density, so much, you are going to worsen the tension between CMB and weak lensing data. This is the so-called S8 or sigma 8 tension. And you can see it. So the question, first of all, is why does early dark energy want such a high dark matter density? And the reason has to do with the early ISW effect I showed you before. So let me take, instead of showing you the full CMB power spectrum, let me just plot the early ISW part of the CMB power spectrum. And if I take lambda CDM in black, and I take early dark energy with the same value of the dark matter density as in lambda CDM, you see you get a roughly up to almost 20% excess in the early ISW effect, which is totally excluded by my previous analysis. If I raise the dark matter fraction from 0.11 to 0.13, you see early dark energy predicts almost no early ISW excess. This is much more in agreement with observations. So the takeaway message is the increase in dark matter density, which is at the heart of the debate as to whether early dark energy really works with the Hubble tension, is due to the early ISW effect. It's there because early dark energy has to match lambda CDM's prediction for the early ISW effect within error bars. And this problem is not limited to early dark energy, but to any model which increases the expansion rate before recombination. Now, maybe the solution to the problems with early dark energy requires more new physics. Let me show you what's one possibility. And if I take the meta-power spectrum predicted by early dark energy with the high dark matter density, you see it predicts an excess of power of roughly 30% in this wave number range, which is the one of interest to large-scale structural measurements. Now, if you look at this shape over here, for those of you who have worked on massive neutrinos, this should look very familiar. It's very similar to the suppression in power massive neutrinos give you on small scales, except it's opposite in sign. So what we thought with some colleagues in Cambridge, George Evstathiou, Blake Sherwin, and my student Alex Reeves, was that maybe if we add massive neutrinos to early dark energy, we can bring this, this excess power down to zero, and therefore remove the problems between early dark energy and large-scale structure. And you see from this plot, you need roughly a neutrino mass of 0.3 eV, if you look at this curve, if you want to bring these residuals to zero in this range of interest. Now, it turns out this is a bit naive. It doesn't actually work in practice. Even if you introduce massive neutrinos, you don't improve the Hubble tension. Your posterior on H0 goes from the green curve for early dark energy to the red curve for early dark energy with massive neutrinos. There are many reasons for this, but one reason is that it's actually really hard in current large-scale structure data to accommodate a neutrino mass of 0.3 eV. So the problems with early dark energy essentially are still there. Okay, so far in the second part of my talk, I've looked at early time consistency test of lambda CDM. Now let me, in the final part, look at late time test of lambda CDM and what we can learn about dark energy. So the goal here is to answer the following question. Is lambda CDM really the end of the story at late times? And how can we test lambda CDM in a way which is as model agnostic as possible? And importantly, trying to make the least amount of assumptions about early time physics. And can we learn something about dark energy or the Hubble constant when we do this? And if we think back historically, one very important piece in the puzzle towards understanding our universe was provided by old astrophysical objects like galaxies at high redshift, which were apparently older than the universe. So that's, of course, a paradox. So between the 1960s and 1998, there were often reports about galaxies which were older than the universe at redshift 1, 2, and so on. Now, of course, there are two possibilities here. Either you got the ages of your galaxies wrong, or the universe is older than you expect. And it turned out to be the second one in this case. And the reason was dark energy. Once you put dark energy in your picture, the universe becomes older at any redshift. Now the question is, so in these years, these old astrophysical objects were very important for cosmology towards essentially showing the need for dark energy. And after the year 2000, they were sort of forgotten. The question we ask in a recent paper with Avi Loeb and Fabio Pacucci is, can old astrophysical objects be important again for cosmology in the 2020s? And can they teach us something about dark energy and possibly the Hubble tension? And the answer is yes. And how does this come about? To see why this is important, we can look at the age-redshift relationship. This gives you the age of the universe at any redshift. And you see this relationship depends on a certain integral, which scales like 1 over h0. This is important because it means that if I impose that the universe has to be older than a certain amount, older than any of its oldest objects, this is going to set an upper limit on h0, which means if h0 is larger than this limit, the universe is going to be too young at any redshift. The other reason why this is important is that this integral does not care about early time physics. This integral gets most of its contributions at redshift less than 10, which means that you can use this as a consistency test of lambda CDM, which is totally independent about any assumption about early time new physics. The early time cosmology can be lambda CDM, it can be early dark energy, it can be whatnot. This integral doesn't care about it at all. And the interesting way to use this as a consistency test is, okay, we can get an upper limit on h0 from this test, if this upper limit contradicts the local measurements from Adam Rees, for example, this is going to tell us that there's the need for some new physics at late times, okay? Because this integral only cares about late times. Now, of course, there's a huge caveat in all of this, that the ages of astrophysical objects at high redshift are extremely hard to estimate in a robust way, okay? So you have to keep this caveat in mind in all my following results. So what we did in this paper was we went through the CANDLES catalog. So CANDLES is a catalog of high redshift galaxies up to redshift roughly 6. They measure the spectra of millions of galaxies. And they also estimate the ages of galaxies in many, many different ways, at least 15 different ways. So what we did was we compiled a catalog of the oldest galaxies in any redshift range. And that's what you see over here. This is essentially a census of the oldest inhabitants of the universe at any redshift, up to redshift roughly 8, okay? And we can use this now to set an upper limit on H0. And interestingly, what we get is an upper limit at 2 sigma of H0 less than 73.2. Of course, I'm missing the units, the usual units here, kilometers per second per megaparsec. This is interesting because it's in mild tension with the local measurements from calibrated supernovae. So the latest measurements give something like 74 plus or minus 1.2. There's a roughly 1.5 to 2 sigma tension between our upper limit and the local measurement. If we take this seriously, what is it telling us? Again, with the huge caveat that these ages are very hard to estimate, if we take this result seriously, there could be 3 possible interpretations. The most boring interpretation is that this is simply a fluke or a systematic. You know, one should not get too excited about 2 sigma events. Another possible interpretation is that maybe lambda CDM is not the end of the story at low redshift. Maybe we need some new physics at late times, which is going to raise the Hubble constant. And one example, which is actually, I think, of particular interest to some people in the audience, is if we take this number seriously, you need something like phantom dark energy or interacting dark energy, interactions between dark matter and dark energy, to get H0 up and fix this problem. Now, another more subtle interpretation is that maybe there's nothing wrong with lambda CDM at late times. Maybe the Hubble tension is not a cosmological tension. It's not a tension between high redshift measurements and low redshift measurements, but it could be a tension between local measurements and anything non-local, anything cosmological. And this interpretation, number 2, has actually been supported by a number of recent papers. In any case, if we look at the bigger picture here, if we look at the picture combining this late time test and the early elSW test I showed you before, I think what's emerging is a picture where it's really hard to solve the Hubble tension using early time new physics alone. And there are many papers recently which have been arguing this in a totally independent way. I point out especially this paper, which appeared in a Nature journal earlier this year. So we often hear, I think we often hear in the community this over-repeated sort of mantra that if you want to solve the Hubble tension, you need early time new physics alone. I think this statement is oversimplistic in the best case. We might need, for example, a combination of early time and late time new physics or some local new physics. But I think really early time new physics alone is going to have big problems solving the Hubble tension. And I hope this consistency test I've shown you will convince you of this. So I've come to the end of my talk. Let me just leave you with 2 key plots from the 2 halves of my talk. In the first half, I hope I've convinced you that there's a lot of potential for looking for dark energy on Earth, especially in big underground experiments, which are usually devoted to searching for dark matter. So we can actually hope to do direct detection of dark energy, especially in the next years. And on the other hand, I hope I also convinced you that it's important to perform consistency tests of our cosmological models to learn about dark energy in a way which is as model agnostic as possible. But overall, the one takeaway message from my talk, I hope, is that there's a lot we can learn about dark energy beyond standard cosmological approaches to search for its gravitational interactions. There's much more we can learn about dark energy, I think, by going off the beaten track in the next years with much more precise data, both from cosmology and astrophysics and from terrestrial experiments. And really, when you put all these pieces together, I think we can hope to unlock the puzzle of dark energy from a multi-probe point of view. So I've come to the end of my talk. I'll thank you for the attention, and I'm very happy to take questions at this point.
So yeah, I have other extended discussion, but my first question, actually a simple one here, is that you have mentioned that only modifying the EDD or any kind of early process would be very difficult to resolve the Hubble tension. I think the key thing in that argument is that you have to change the omega matter, mostly omega CDM. So, I mean, those papers which you have shown, I mean, show that in their paper, if you change that, then you will be able to produce a pretty high value of sigma 8 and also OVM production, so that it will just make it even harder to be consistent with the larger structure measurement. But what if you don't change that? What if you kind of involve new physics, which kind of change the sun horizon early time, but keep that value to be the same or almost the same? In that sense, the low redshift data would be fine, would be able to reconcile, whereas you can kind of still resolve the early kind of Hubble, I mean the sun horizon issue, so that it will just reduce Hubble tension. So that is my
yeah. Can you repeat the last part of your question? I missed what you were saying about only early time new physics. The last part, can you repeat it?
Yeah, so my last part is that the argument why this reducing cosmic sun horizon cannot resolve Hubble tension is because this will change the omega CDM. Right?
Yeah,
it will change the CDM fractional number density, so that it will make the later structure growth sigma 8 to be changed, so that it will make it even worse.
Even worse, yes.
So my point is that what if you keep that to be the same? What if you invoke new physics that will just, in the other way, reduce the cosmic sun horizon, but still keep the omega CDM to be the same? In that sense, you can avoid this problem and still in some way to solve the sun horizon problem, and therefore H0 tension.
Yeah, I see what you mean, but the problem is that generically, when you introduce new physics, which raises the expansion rate, again, you are going to raise the early SW effect, like with early dark energy. And the only way you can compensate this, the most obvious way, is to raise omega C. And so this is well known for early dark energy, but it's the case for many other early time models. I think that the paper by Jedamzik and others shows a very clear plot. So it's almost inevitable, the moment you put new physics at early times, it's almost inevitable that you have to raise omega C. There are examples of models which avoid this problem. One of them is the strongly interacting neutrinos, but they run into problems with other data like CMB polarization or lensing. There is, as far as I know, no model which really successfully fits all the data at the same time, as far as I know. Both at early and late times, yeah.
So are you saying that because the reason is if you invoke any new physics at early time, then you essentially have to increase your omega C, so to compensate its enhancement on the early SW?
Precisely. This is the most direct way of lowering the early ISW. You can find other ways. There are of course other ways. You might have to invoke a more complicated early model. I don't know how familiar you are with this, but there is a model called new early dark energy, where you have two dark energy fields. You have a multi-field model. And what happens is you get new contributions to the early SW effect, which partially cancel this. So this model doesn't require such a high omega C. It still requires a higher omega C, but not as high as in the early original model. So the thing is, either you need to raise omega C, or you need to cook up a more complex dynamics in your model, such that you reduce the early ISW effect. But the point is, the most naive models are going to enhance the early ISW, as I've shown here. And this is a problem. This is not something you can tolerate. Not in Planck data, at least. Maybe in ACT data, there might be a sign of this, actually. And I think I had a small line hinting to this, okay? There is, if you take it at face value, there is sign of new physics in ACT data, but not in Planck.
So in Planck, that range of L 50 to 300 is really sort of the data really kind of attached to that theory curve, and there seem to be no space have any improvement. But for ACT, there seem to be, as you said, I mean, I never peer into that range of data before, but in ACT, you said there's some like a bit space, a big gap in between the theory and data.
Yeah, well, if we take, the point is, if we take ACT data at face value, if you extrapolate down to the first peak is roughly a bit higher than Planck. It's like 2 sigma higher, a bit more than 2 sigma, which is the reason why ACT wants values of NS, omega B, but also N effective, which are a bit off from Planck and from lambda CDM. The reason is essentially there's a mismatch in the first peak. And so whatever new physics couples to the first peak, you will find evidence of it in ACT. One example is early dark energy. There was a recent paper in ACT led by Colin Hill, where they claim evidence for early dark energy at something like 2 sigma. If you take ACT data seriously, that's what you get. Of course, the question is, of course, whether there is systematics. I know there's ACT people here in the audience, so I won't go into this because I'm not the expert. But that's the big caveat, of course.
Oh, that's something very interesting. Yeah, this is a primary range of signal. I mean, at this level of precision, any deviation would involve interest in,
Absolutely.
to see whether there's some
but the thing is, the tension between ACT and Planck means that only one of the two can be right. It's not that there are 2 experiments measuring related quantities. No, there are 2 experiments measuring the same thing. So either they agree, or at least one of them is wrong. I think that's the most correct way to phrase it. I don't know who is right, of course.
Okay, I see. Interesting. Yeah.
Okay, thanks, Injo. Are there any more questions? I encourage the students to ask some questions.
Yeah, our students should be more active in raising questions to the speaker.
I don't bite, don't worry.
Maybe I can ask one quick. For the first part of your talk, you spoke about the solar chameleons and these constraints from the sun. How dependent are these constraints on one's choice of Bayer potential? Because the chameleon potential. Yeah.
So what we did was we took an inverse power law potential. We took n=1 chameleons, and I think you worked with Amanda, so you probably know what I mean. And we took this n=1 chameleons because they are the most constrained. Okay, so we didn't want people to come to us and say, "Hey, you want to evade constraints." So what we did was to explain this excess with n=1 chameleons. We can do it with parameters which are totally allowed by experiments. I would say the strongest constraints are on this beta gamma, the coupling to photons. And you get constraints from CAST. So this is a helioscope at CERN, which is looking for chameleons from the sun, exactly. And there's an upper limit of beta gamma less than 10 to the 10. All the other parameters are totally in the range of what's allowed by observations. So if we took a different Bayer potential, the results don't change. In fact, we tried other values of n, and there were essentially no changes. The results are essentially insensitive to that. What changes is that you get, in principle, wider ranges of parameter space available. So you can actually fit your signal potentially even better. So what we consider is the most constrained model, actually. But that's simply for, because n=1 has been the most studied model. In principle, there are many other constraints on n different from 1. It's just that people have not studied them as in depth as the n=1 model.
Okay, good. Thanks.